Hello and welcome everybody to Advent of Code 2023 day 16. So today wasn't too tough of a challenge. I was a little bit late getting to finish it just because I was busy, but it wasn't actually that difficult. So my late publishing of my video today isn't because it was super hard, it was just because I was busy and didn't get around to being able to finish it until now. So yeah, it was kind of it was sort of fun. It was pretty fun. There was some kind of fun little patterns in it. My solution is, I think it's probably a little bit verbose compared to what it could be, but I enjoyed doing it. I thought it was kind of a clever one, and it didn't end up being like really disgusting one like day 12, which sort of reminded me. It sort of felt like it was going to be very like day 12, but it actually ended up being a good bit simpler for me anyway. So yeah, with that said, let's look at the problem and look at some code. So, day 16, the floor will be lava. So, from our last one, we focused all of our lenses and stuff, and it seems to have focused somewhere. So we follow the reindeer to deeper into the lava production facility, and basically we end up in a big cave, and we're at the very heart of the mountain, and we find where the beam of light is coming into, and it's basically coming into all of this big grid thing of mirrors, and the thing is aligned so that the beam of light comes into one part of this array of mirrors, and then it bounces around all inside this array of mirrors. So we're told this is our setup. Dots are empty spaces, and then the angled slashes, so forward slashes and back slashes, are angled 90-degree mirrors. So for example, if a beam of light was to come in this way, hit the mirror from here, it would go downwards, and then if it was to come in from this side, it would go upwards, and then the other slant of the mirror has the opposite effect. We're also then told that there are these, there's pipe symbols and minus symbols, and these are splitters. So this is where I thought we were getting into the day 12 territory, where if you were to I figured immediately, I was like, well, okay, we're going to have to walk this path of all these mirrors. And then as soon as I heard about the splitters, so what these do is, if light travels along the length of the line, it doesn't do anything, it just basically passes straight through it. But if it hits from the side, it splits the light. So for these vertical ones, if it hits here, it splits the light to go, one path will shoot up and one path will shoot down, and the opposite case for the minus symbol, if it hits from here, one will go right and one will go left. So that's basically it. That's pretty much all they tell you. So they tell you a starting point, and yeah, so the thing is, so they tell you where to start, and basically you have to trace the path of the beam. What it says is, everywhere that the beam, so each tile or each cell that the beam passes through is then said to be energized. So our job basically is to simulate this path of the light through all the mirrors, and then figure out how many tiles are energized. So if you want to think about this as walking, a graph, basically what we're trying to do is we're trying to count the unique number of tiles that have been visited by our algorithm that walks. And that's it. We're also shown basically that you can visit a cell multiple times, or a tile, whatever you want to call it. In their example here, they trace out the path of a light beam going through, so it comes in from the top right, and it shows us the direction that they move. And then there's numbers in places here where the path crosses that tile multiple times. So we're told that can happen, but it doesn't do anything. It doesn't affect anything. And what else are we told? Yeah, so that's pretty much everything we're told. Now, one thing we're not told, but it is in the example, is that there are loops. And that's basically this is where the crux of the problem is. So if you just try to simulate this, and say you did it with like a recursion where you're just going through the whole thing, you basically end up in like an infinite loop, because there are paths when they come in that you follow them through. Some of the paths terminate by going out to the side here, like this one here, and you can see this one here terminates by just going off the edge. So if it hits that side point, there's nothing's going to happen. It's going to leave, or nothing's actually going to happen to it. So that's fine. But then some of the paths will loop back around to some point and then continue on forever. So by continually simulating that, it doesn't that's not going to give you any different answer, because you're still visiting the same number, but it makes it difficult to figure that out, because it'll just keep going. So how do you tell it when to stop, or how does it know when to stop? That's basically the crux of the problem. So with all that said, let's have a look at the code and see how I implemented this. So there's a few things. I'm going to come back to this big mess up here, but let's start. So let's start down here. So actually, we won't start here. Oh, maybe we will. Okay. So the first thing I decided I wanted to do was I wanted to model the direction that we're traveling, and when we encounter a symbol that's a mirror or a splitter, I wanted to be able to model, well, what's the next direction that we're supposed to travel in. So for all our angled mirrors, we know that if I'm coming at it from the right, which is this rightmost direction that I'm looking, I know when I hit that type of mirror, the next step is going to send me is down. So I've modeled that as this array with a down. So why it's an array, you'll see down here. So for the same, so this is just correctly typed out. So I just looked at them visually and just typed out what these map to. And then the same for the pipes, did the same thing, except for these, we know that these splitters, they'll go, if you come in from the left, it'll go up or down. If you come in from the right, it'll also just go up or down. And then if you come from up or you come from down, they don't do anything. So they behave just like dots. In that case, they're transparent. And the same is the case for the minus sign. So with that modeled, the other thing that I wanted to try and do was I wanted to try and model taking the steps around the grid using the similar kind of notation, using these like symbolic notations that Ruby has. So for that's what this thing is for. So this looks a bit crazy, but I'll just need to really explain it for one of them, because they're all the same, just tweaked slightly. And previously what this was basically just an incrementing thing, so that if I started from a cell, I just want to go to the next cell, and then the next cell, and then the next cell. So this was just a direction thing, which we've seen before, where it's like x plus 1 means going to the right. So y staying the same and x plus 1 means going to the right. And then, x minus 1 is going to the left, and then y plus 1 is up, y minus 1 is down. So it was basically just a little four-way check that just returned the new coordinate based on passing in what the current coordinates are here. But that, I determined that taking one step at a time was a little bit of a waste in terms of recursions that we're going to be doing, because I decided to do this with recursion. And if you're just walking one step at a time, that's kind of a waste, because most of the grid that we're looking at is empty space. So the input doesn't really show you this, because the input is fairly sparse, but there is a lot of these are sort of close together and it's quite small. So you're like taking a few extra steps, so incrementing one step at a time through these dots isn't that bad. But on the actual input, which I can, if I open up the actual input, you'll see it's big. So the grid is quite huge, and there's lots of empty space for the beams to travel. So just incrementing one at a time wasn't going to be a good way to do this. So instead, this logic that I implemented is basically from my current cell, look all the way, if I'm facing the right direction, look all the way to the right as far as I can see, and if I encounter a non dot cell, then that's the next cell that I want to go to. So this is the equivalent of, so for this input, say if we're here and we're looking down the way, or say we're here and we're looking down the way, we'll go skip all of these cells until we get to this one, and then that's the next one that I pass in to go to the next recursion, and then I just mark all these cells as visited in the data structure that I'm using. So that's all this does, and it does it 4 different ways because there's 4 different directions that we need to look, and this is just the X and Y logic is all this different in all of them. You could definitely simplify this, but I had written it out, I did it once and then just copied it and adjusted it slightly. So that's all that does. I'm going to minimize it because it's not, it just does this thing. So then I suppose to set up my data in the first place, I'm going to read through the file, read each line, and I'll use my hash map, my favorite way to model this. So I've got my X and my Y coordinate as the key. I store the character, and I also store this count, which is going to be the number of times that it's visited. It doesn't actually need to be a count. I originally had this as a Boolean, and then while debugging, I moved it to a count so that I could try and visualize how many times cells were being hit to check that off. But it's immaterial. I just left it as a count in the end. So then we're going to walk this map. And as we walk the map, we'll be modifying this data structure for each cell. So when it's visited, we'll increment this. And then at the end of this, we should have a map here where all the visited cells have a non-zero value for their visited property. And then this little select statement down here just pulls out all of the visited that are non-zero and counts them. And that's our number of energized tiles at the end. So inside the recursive loop, it's pretty standard. There's 3 different cases of when we will recurse. So the first one is when you hit a star point, or when you hit hit a pipe that's either vertical traveling vertically or horizontal while you're traveling horizontally. Then we use that lookup above here, which checks here, and it says we get a blank because we're, say, traveling left or right. And then that's a case where it's basically treated as like a dot. So for that instance, we just go get our next coordinate that we want to move to, and we'll walk there and we'll pass that in. The other cases then down here, this is where we encounter an angle. So to deal with, this is just all the other cases. So this is where you hit a splitter and it'll split one way or the other. So you need 2 ways to go. Or we'll just hit an angle one, and in which case there is only one way to go. So only one of these will be non-nil. So we'll go that way. If you hit a splitter, they will both be non-nil, so you'll do 2 more recursions, and this is where you form a branch in your recursion. So yeah, that's it. This is where we use those directions. So that's where we use these lambdas that were up here to calculate what the next XY coordinate we should go to is. So effectively what that'll do is, if I'm here and I call that lambda function, it'll return this ID for me, and I'll know that's the next ID that I recurse to, and it'll also handily fill all of those for me, so I don't have to worry about updating them. Okay, so the break conditions for this is where it gets important. So the map, firstly, we're just passing the map through the whole way through as it is, because we want to make sure that we're, no matter where we are in our recursion along the tree, we want that data structure shared between everyone, so that everyone can update that visited count, so we don't end up with multiple copies floating around. And then so also with that map, then the exit condition that we get for that map is if the cell that we're going to move to next is outside of the map itself. So this is, we've gotten to the edge and we're about to go off the edge of the map, so there's no coordinate there. So then we can exit because we know we've reached the very end and we're not going to go any further. And then The final exit condition, and this is so with just that exit condition, we can end up in an infinite loop. So this doesn't take care of the case where we, at some point, so we start moving, we hit a point, and then to that point we'll keep looping around to it. That will spin forever now with just this being our only exit condition. So we need to add one more thing to make the exit condition work. So for that, what I've done is I've created this other hash that we pass in at the start. That starts off as an empty hash, which I call the visited hash here. And so the visited hash is going to be a unique key that is the two coordinates, the x and y coordinate of the cell that we're on, and the direction at which we entered that cell. So the real thing is, as you're going through a loop, you need to know, well, how do I know I'm back at the start of that loop again somewhere? And the way you do that is that the direction that you traveled through that cell the last time will be the same. So that's the key for breaking this loop. So that's how you know that you're definitely back at where you started, because you're entering a cell in the same direction that you entered it previously. The only way that can happen is if you're in a loop, and that's how you know you're back in a loop, is that you've entered that cell from the same direction again. So that's our break clause. That's the last thing we do here. So we maintain this big list or this hash of these visiteds, and we pass that down throughout the whole thing, because say you could have multiple loops that would all sort of cross over each other, and they should all share this, because if you've entered from that side, then you know that's it. You're use your words, Ian. You know you're stuck in a loop. You know you've already passed through this, so you don't need to go there again. So you don't need to try and visit it again. And that's it. So once these exit conditions are met, we'll exit, and then we'll have our map here, and we can do this sum, and that will give us the right answer. There's also a little bit here, you don't mind about that. It's just some visualization code I was using to debug some stuff earlier on, but I've just left that because it's not really pertinent to the solution itself. So yeah, let's have a run of that. 16 part 1, run on the sample, and it runs in a few microseconds, and 46 is the answer for the sample. Then if we run it for our input, we get, and that is the right answer, and it runs in 43 odd milliseconds, which is not super fast, but it's pretty quick considering what it's doing. But yeah, it's not crazy fast. So yeah, that's everything for part 1. So let's have a look at what they want us to do for part 2 now. So part 2. So for part 2, yeah, so this basically what we're told is this is wrong, or it's not enough energized tiles. So the reindeer pulls you over and shows you that there's a thing you can do where basically you can like move the collection of mirrors around, so that, or the beam of light that enters, you can make it enter from any direction. So it starts outside the grid and it has to enter at one point. So from along the top, it can enter from any cell along the top. Along the right, it can enter from any cell along the right. The bottom and the left, all the same. So, and it's the exact same problem that they've asked you to do. Is what they've asked you to do is, well, what's the biggest amount of energized tiles I can get if I test every one of those paths? Which they've not really changed the problem at all. And if you ended up with a relatively efficient solution, like I did here, the sort of, making up in the ante for the second part of the problem, they've not really done it, because they've actually given us quite a limited set to do. And the reason for that is because there's just not many, different options. So if you look at this 10 by 10 grid, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 along the top, and then you can have 10 along the bottom and the right. So it's 40 options. So effectively, to get the answer for this one, you just have to run the exact same algorithm we have 40 times, and you've got your answer, and that'll be it. So whichever one is the largest will give you your answer. And the same thing happens for our big grid, except our big grid, well, mine, I don't know what size everyone's is, I'm assuming they're all the same size. Mine is 110 by 110, so that's 440. So that means that I have to run this algorithm that gave me this answer 440 times and take the biggest one, and that will be my answer. So I did that, and it works. There's probably a clever way you could do it to like really speed this up, but the brute force for this is trivial. So yeah, I was fine with it. It takes a couple of seconds to finish. If you do the quick maths on that, you'll see I think it should work out to be like, no, something like 10 seconds or something like that it should take to finish. And it does. So like this code is literally identical. I just have these 2 loops in here that do, and we do this 4 times for the 4 different directions with the from 0 to x max and 0 to y max, and that's it. It gives you the right answer. So I run that. If you run it on the sample, you see it's a trivial amount of time that it takes to run. The first one did take microseconds, so it's basically 40 times that is what the runtime is. And then the same for my input. Hit run on that. It'll sit here for a couple of seconds and it'll output its answer. Let's see. Ooh, there we go. 11.46, yeah, about 10 seconds. So there you go. That's it. I think I was thinking about this, and I was thinking that maybe you could speed it up by sharing by basically sharing a cache for what the paths look like, because it doesn't matter where the light entered. If it hits a path that you've already been on, then if you've been on that before, you know what's going to happen for the rest of the loops. Because it doesn't matter how it entered the grid. Once it's in the grid and it starts bouncing around all the mirrors, then if you find like a path, like a loop that you've already seen before, that will be the same regardless. Because if light enters a cell at a specific direction, you know that's always going to give you a certain answer. I would have had to architect my solution slightly differently to take advantage of that, I think, but it's kind of trivial, I think. But yeah, that's it. Surprisingly okay. Day 16. Thought it was going to be a little bit harder at first, and then the second part was more or less trivial to implement. Granted that my first solution was relatively fast, so if my first solution hadn't been as fast, then maybe this solution wouldn't be as viable. But I don't really know if there is another way that you would do this that would be like super slow, and then you wouldn't be able to do this for part 2. I imagine that any decent solution for part 1, the part 2 should just be trivial to solve, really. So that is it for today. I have another very busy day tomorrow, so I don't know if I'm going to get much coding done, so fingers crossed for another relatively easy problem so that I can get it done in the day. But yeah, that's everything for me today, so I will see you guys tomorrow, hopefully. Bye bye.